Welcome back to Revise and Resubmit, and welcome to another weekend book review. I'm Pavlov.
And I'm Nikita.
Okay, let's dive right in. Picture this. You're watching whitewater rapids, right? Turbulent, unpredictable.
Yeah, chaotic.
Now, kind of flip the switch in your mind and think about the stock market. You know, the sudden spikes, the unexpected dips.
Seems like totally different worlds.
Exactly.
Huh?
But what if, and this is the wild part, what if the same mathematical tools we use for understanding that swirling chaos of fluids could actually unlock some mysteries in finance?
You're talking about using fluid dynamics math for stock options.
We are. Specifically, something called Kelvin waves. These are fascinating mathematical patterns first found in fluid dynamics. And the surprising thing is how they connect to something as complex as, say, pricing a stock option.
It does sound a bit mind-bending, doesn't it?
It really does.
What's truly remarkable, I think, is this unexpected link. I mean, we've seen math move between physics and finance before, sure. But this deep dive we're doing into Alexander Lipton's work, Hydrodynamics of Markets, it reveals a really elegant connection through these Kelvin waves.
Right.
They were originally explored by Lord Kelvin, way back, late 19th century, to understand how disturbances move through fluids. But these wave-like solutions, they turn out to be incredibly versatile.
Versatile is the word. And this isn't just, dusty old theory locked away somewhere.
No, not at all.
As we're about to explore, this whole framework gives us a fresh look at foundational financial models, like Black-Scholes, and even the more complex volatility models, Heston, Steinstock.
The standard toolkit, really.
Yeah. And it even gets into the super modern world of cryptocurrency, helping us understand that kind of head-scratching thing called impermanent loss for automated market makers.
Which is a huge topic in DeFi right now.
Absolutely. And believe it or not, it loops back again to describing how tiny particles move.
It's quite the range.
So our mission here today is basically to unpack the core ideas, maybe demystify some of the math a bit, and really shine a light on these genuinely surprising connections. Water flowing, money moving, linked by math.
And the core insight, it really lies in spotting these fundamental mathematical similarities. Lipton's work shows that lots of problems in finance and physics can be boiled down to similar underlying structures.
Okay.
We're talking about things called affine differential and pseudo-differential equations. And the key thing is, these types of equations, they have solutions that take the form of Kelvin waves.
Okay, so when we hear Kelvin waves, maybe don't picture actual ocean waves.
Right, exactly. They're more abstract. Mathematical solutions, really.
And the document mentions something called the affine ansatz, which, sounds a bit intimidating.
It does sound fancy.
But think of it as like specific mathematical shape or structure.
Yeah, a specific, elegant form. And the paper points out that this is actually a particular kind of Kelvin wave. And that observation, that seemingly simple point, it acts like a kind of secret code breaker.
Yeah.
It connects these areas that on the surface seem to have nothing in common.
That's the really interesting bit. It bridges these gaps.
If we sort of step back for a second, think about Isaac Newton. His development of calculus differential equations that gave us the language for physics, describing motion, forces.
The foundation for so much.
A monumental unification, really. And what this framework we're discussing aims to do is, in a way, similar. It's trying to unify understanding across different fields, physics, fluids, finance, by showing they share these deep mathematical descriptions.
Description solvable using these Kelvin waves.
Precisely.
Right. So Newton gave us tools for planets. Now, this framework builds on that legacy, offering a comprehensive mathematical toolkit using Kelvin waves to calculate things like transition probabilities and expectations.
Yeah, and that's crucial. Basically, figuring out the likelihood of a system moving from one state to another over time.
In all these different systems.
All these different systems, yeah. And if you can get a handle on those probabilities, you fundamentally understand the dynamics of the system.
Makes sense.
The document really emphasizes that this gives a consistent, unified way to study these probabilities for a whole range of what are called affine processes.
Okay, now for the part that probably grabs most people's attention. How does this actually translate into, the world of finance? Let's start with something pretty familiar, option pricing.
Right.
We mentioned Black-Scholes, Heston, Steinstein. How do Kelvin waves fit in there?
Well, within this framework, Kelvin waves become super useful for analyzing these standard models. The math structure of these models actually lines up with the kinds of equations that have Kelvin wave solutions.
Oh, okay.
And what's fascinating is if you look at black skulls through this Kelvin wave lens, you can get a more maybe intuitive feel for how volatility shocks, sudden changes in actually ripple through option prices.
Almost like waves in a pond.
Sort of, like disturbances spreading through a fluid. It offers maybe deeper insights into the dynamics hidden in these models.
And does it go beyond the basic models? You mentioned more complex situations.
Yes, it extends to things like path-dependent volatility.
Okay, path-dependent, meaning volatility isn't constant. It depends on how the price got there.
Exactly,
Yeah.
which is much more like real markets, right? Volatility changes, and how it changes can depend on its own history. The framework can handle that too.
Wow. Okay, so that covers standard stuff. What about the more exotic instruments, things beyond simple calls and puts?
This is where you really see the power and the versatility of the approach. The document talks about using it for Asian options.
Right, those depend on the average price over time, not just the final price.
Correct. And also things like volatility and variance swaps contracts where you're basically trading volatility itself.
Trading volatility.
Interesting. And bonds, bond options too. The unified framework provides this consistent mathematical language to tackle these trickier instruments.
Okay, Asian options, vol swaps.
Yeah.
These are maybe more for sophisticated investors. But you also mentioned something incredibly current, cryptocurrency.
Yeah, the AMM application.
Automated market makers and impermanent loss. That's a huge topic right now.
Yeah.
How do Kelvin waves help there?
Well, this is definitely a cutting-edge application. AMMs, they use algorithms to set prices in crypto liquidity pools.
Right.
And impermanent loss. It's that frustrating thing where the value of the crypto you put in the pool ends up being less than if you just held on to it.
Yeah, it drives liquidity providers crazy.
Exactly. The research suggests that this Kelvin wave framework can be a valuable tool in figuring out strategies to actually hedge against that loss.
Really. So managing risk in DeFi using math derived from fluid dynamics.
Potentially, yes. It's offering new ways to think about risk management in that space.
Wow. From 19th century fluid physics to hedging crypto losses today. The range is just striking.
It really is.
Now, the document also mentioned this framework isn't stuck with the usual nice, well-behaved math models. It can handle non-Gaussian processes.
That's right. So systems where random events don't follow that standard bell curve distribution. Real-world events often have fatter tails, more extreme outcomes.
Which is definitely true in finance.
Absolutely. And it can also handle processes that are either degenerate, basically, more moving parts than sources of randomness, or non-degenerate.
Okay.
And furthermore, it introduces this idea of augmented processes, where you take a basic process like Brownian motion and you expand it by adding related variables.
Like what?
Well, the example given is augmenting Brownian motion, which leads you to something called the Kolmogorov process. It shows how the framework connects different types of these stochastic processes.
So it seems like a really adaptable, powerful set of tools. And speaking of the Kolmogorov equation, the document highlights something pretty significant there, a correction.
Yes, that's quite notable. The analysis in Lipton's paper actually identifies and rectifies an error, a subtle but important one, in Kolmogorov's original solution.
Wow, in the original solution.
Yes. The corrected solution is shown to be dimensionally consistent. The units match up properly, it scales correctly with parameters, and it lines up well with numerical simulations.
That's fundamental. It really underscores the rigor here.
It does. It shows the potential for refining even foundational equations using this approach.
And there was another unexpected connection mentioned, wasn't there? Something about vorticity in fluids and particles on springs.
Ah, yes. That's another truly remarkable finding. A similarity between how vorticity, think of it as the swirling motion in a 2D viscous fluid, how that spreads or propagates,
Okay.
and the motion of a particle that's bound by a harmonic force, like classically a mass on a spring.
Those sound like they belong in completely different physics lectures.
You really do. But this similarity allows the researchers to derive a new explicit mathematical expression for that vorticity in the fluid. And it turns out to be expressed in terms of a Gaussian density, like a bell curve.
Just another example of these deep, surprising mathematical links.
Exactly. Uncovered between systems that look totally different on the surface.
This just keeps getting more fascinating. Now, the document keeps coming back to the affine framework, or the affine ansatz. Why is that specific approach so central?
The affine framework gets highlighted because it's, particularly powerful and versatile, it gives a structured way to apply these Kelvin wave solutions across a really wide range of models.
So it's like the practical toolkit within the bigger theory.
That's a good way to put it. It's pretty comprehensive, it handles lots of situations, and crucially, it's often mathematically tractable. You can actually work with it, even when the problems get complex.
Okay, that makes sense. So if someone, say, a quantitative analyst, wanted to actually use this Kelvin wave approach, what are the basic steps? The document mentioned 3.
Yeah, at a high level, it outlines 3 main steps. First, you need to formulate your problem, maybe pricing some instrument or modeling a physical system in the language of these specific affine differential or pseudo-differential equations.
Get it into the right mathematical form.
Exactly. Second step is finding the right Kelvin wave solutions that actually fit those equations for your specific problem. And the third step is using those solutions to calculate what you actually care about, the option price, the probability of default, whatever it might be.
Formulate, solve, calculate. Sounds straightforward enough on paper, probably harder in practice.
Well, yes, the details can get quite involved, naturally.
Let's circle back to some of those fundamental equations we touched on. We mentioned Kolmogorov again. In simple terms, what's it describing, and how does it relate to the Klein-Kramer's equation?
Right. The Kolmogorov equation, it pops up all over the place, really. It essentially describes how the probability distribution of a system, like the probability of it being in a certain state, evolves over time.
Like the probability of a stock price being X tomorrow.
Kind of, yeah. Think of it as tracking how the likelihoods change. Now, the Klein-Kramer's equation comes from statistical physics. It's a more detailed model specifically for particles moving around in a fluid-like medium.
So it includes things like friction, random bumps from molecules.
Exactly. It accounts for viscosity, random thermal jostling, external forces. And interestingly, the Kolmogorov equation can actually be seen as a special case, a simplified version of Klein-Kramer's.
How so?
You get Kolmogorov from Klein-Kramer's under specific conditions, basically when you ignore friction and external forces. So Klein-Kramer's paints a more complete physical picture in that context.
I see. And the document mentioned Chandrasekhar, the famous astrophysicist.
That's the one. Subramanian Chandrasekhar, a Nobel laureate. He found some really elegant solutions to the Klein-Kramer's equation back in the day for both free particles and particles bound by that harmonic spring-like force we mentioned.
Using clever math techniques, I assume?
Very much so. His work was foundational. This more recent research builds on those results, often expressing the solutions in forms like explicit Gaussian distributions that are maybe more directly useful for applications.
Got it. Now, you hinted earlier that this isn't just for smooth, continuous changes. It can handle jumps, discontinuities.
Yes, that's another important extension. The framework can be generalized to handle stochastic processes that involve sudden jumps.
Which happens all the time in markets. Sudden news crashes.
Precisely. The document gives an example of a Feller process with Poisson jumps, basically. Random jumps happening at random times where the size of the jump follows an exponential distribution.
Okay, so it brings in another layer of realism.
It does. And it also extends to models with stochastic volatility.
Where volatility itself bounces around randomly.
Exactly, which gives a more unified way to look at models like Heston and Steinstein, where vol isn't constant.
We've definitely covered a lot of the theory and the connections. Maybe we can bring it back down to earth with some concrete financial examples. The paper mentions forwards, European options, Asian options.
Sure. For simple forward contracts, the framework confirms the standard pricing based on spot price, time, interest rates, dividends, or costs of carry. Nothing too surprising there, but it fits. For standard European options, calls and puts, it naturally leads to results like the Black-Scholes formula, providing perhaps another way to derive and understand it via these Kelvin wave solutions.
Right, the cornerstone of option pricing.
Then you get to Asian options. Now, pricing those with arithmetic averaging, the simple average, is notoriously hard.
I've heard that.
But the framework offers a much more tractable way to price Asian options based on geometric averaging, using specific formulas developed within this Kelvin wave approach. Formula 6.45 in the paper for those following along closely.
Okay, so easier for geometric, still hard for arithmetic. That makes sense. What about volatility swaps?
For vol swaps, the fair strike price, the rate you'd agree on today, is basically the expected value of the realized variance over the swap's life. The Kelvin wave framework provides the machinery to calculate those expectations, often under these affine models.
Calculating expected future variance. Crucial. And bonds, bond options.
Here again, the methodology connects financial formulas, to physics. It links bond pricing in certain models to the math used for underdamped Brownian motion.
Underdamped. Like a particle moving through treacle but still oscillating a bit.
Kind of, yeah. It allows applying the framework to price bonds and bond options in standard interest rate models like Vasicek and also Coxinger-Saul-Ross, CIR, though the details for CIR are a bit more involved and maybe less explicitly detailed in the parts we focused on.
Okay. And finally, let's loop back one last time to those automated market makers in crypto. We know impermanent loss is the problem. How does this help specifically?
Right. So the document explains the basics, constant sum, constant product rules that AMMs use to set prices. It talks about how arbitrageurs interact with them, which is what causes the impermanent loss for the liquidity providers.
Okay.
The Kelvin wave framework provides mathematical tools to actually analyze the dynamics of these AMMs, understand how the value of the liquidity provider's stake changes over time, and from that analysis, you can potentially develop better strategies for hedging the risk.
So modeling the risk to manage it better.
Exactly. And it even mentions extending this to mixed rule AMMs, which are sort of more general versions, suggesting the framework is adaptable as DeFi evolves.
Okay, wow. We have really taken a deep dive today. We've gone from fluid dynamics and 19th century physics all the way to cutting-edge crypto finance, all connected by this thread of Kelvin waves.
It's quite a journey.
What are the absolute essential takeaways you'd want someone listening to remember from all this?
I think the key thing is this idea of a powerful, unified mathematical framework, using Kelvin waves to tackle problems across these fields that, seem totally separate.
Hydrodynamics, physics, finance.
Yeah, it really uncovers surprising connections, like how disturbances in fluids relate to option pricing. And importantly, it gives us practical tools to address really complex financial challenges.
Option pricing, vol modeling, even crypto market making.
All within one coherent mathematical language.
It really is kind of an aha moment when you see those hidden mathematical structures linking things up. And the fact that this research even corrected a fundamental equation like Kolmogorov's, that says a lot.
It highlights the depth and rigor, definitely.
So why should you, our listener, find this all so interesting or relevant?
Well, fundamentally, this research provides really powerful tools for understanding and modeling the complexity that's just inherent in financial markets and in stochastic systems generally.
It's not just academic, then.
Not at all. It has very practical implications for risk management, for financial engineering, maybe developing new instruments, and honestly, for anyone just trying to make sense of how these complex systems work, especially as finance and tech get more intertwined.
Okay, so to leave you all with a final thought to mull over.
Yeah.
If the deep mathematical structures governing how fluids flow and how markets behave are this intertwined, what other hidden connections might be out there between fields that seem totally unrelated right now? Could the principles that describe, say, turbulence in fluids give us new insights into the most chaotic, unpredictable moments of market volatility?
That's a fascinating question.
As markets get ever more complex, more data-driven, could frameworks like the one we've discussed today become, essential tools for navigating these uncharted waters and maybe heading off unexpected risks?
It certainly makes you think about the unifying power of mathematics.
Absolutely. If this deep dive has sparked your curiosity, we definitely encourage you to check out the source material, especially Alexander Lipton's Hydrodynamics of Markets, for the full mathematical picture. Thanks for joining us. And don't forget to subscribe to Revise and Resubmit on Spotify and Apple Podcasts for more captivating deep dives like this one. Until next time, keep those minds curious, keep questioning, and keep revising and resubmitting.